and I leave it up to the class all the time. Can you give me some suggested dates?
Monday after next.
Monday the 30th.
Give me the date.
October 7th.
Here.
September 30th is the date. October the 7th is so far away.
It's never going to change.
I don't care.
No, October
Put
the
a
2nd.
different board up. Please go here.
Pull this bad boy up.
Nah, I think we got this.
I'm just gonna believe motions until he agrees with that.
I mean, he's only got one vote.
All right.
I guess I should look at it.
Gonna vote this thing. All right. So it's Monday, Wednesday, Friday. What's the Monday date? September 30th? Did you
Yeah.
say? September 30th.
Or October 7th, Monday.
That's a long way away.
Yeah.
No, it's,
I'll put it down.
it's
Hold on.
September 30th.
That's
Not
30th.
7th.
Pardon me. All right. And then this, this is going to be the week right here. I mean, I'm just going to say it probably makes sense to have it about then in that week.
You
So.
could also have it the Friday before.
Oh, what?
The Friday before that.
No.
No, no, there's no
So-
Friday before then.
That's the 27th. Right?
Yeah. That's,
No. That doesn't exist.
All right, I'm just gonna say this, I don't care, what we're gonna do is, take the top two and run them off if we get a bunch of votes all over the place. So we'll start with the Friday here on September 27th. You want one hand? I see, no, do me a favor, you count with me? Just count. Hold them up there.
1,
5. I got 2, 4, 5. All right. We're gonna run off the top ones. If you want it on Monday, September 30th, one hand, just one. Now hold them up and count. I got 1, 2, 3,
more
4,
than enough to
5,
win.
6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I got 19.
a lot.
yeah.
I really can't, it looks like
If,
a lot.
let's just do this officially one time, all right? Wednesday, you want it one hand. I count
No,
2.
not Kate.
Friday. We're done here. All right, just, I'm out of curiosity, I think we got it here without, unless somebody wants to change their votes, so. It'll be Monday, September 19th. And can you do me a favor? Can you send me an email to remind me?
Yeah, I can do that now.
Second thing I wanna ask somebody to do.
You got it?
Yeah. Shh, hold on, let me hear, what?
Will it cover the same material regardless of date?
Well, you cover, what it amounts to is that you cover everything up to the day before the test. That's just normal, but I mean, it's, at this point, there's an incremental difference. You're not talking about major, like 3 chapters difference. Would you do me a favor? Can you go upstairs to the 2nd floor, in where the administrative assistants are, and ask for a couple of black markers, fresh ones? Would you do that? And I appreciate it. The only reason I'm saying this is these markers are dead, and I didn't bring them, and I kinda need it. Now, are there any questions before I just take off on this stuff? Anyone?
I will help you study on Sunday. I will show up here on Sunday.
Is that one
Yeah,
that
no,
works?
we have
on
three
this?
tests.
Observation?
Yeah.
Yeah.
It works. Let's see, it works. All right, that one will work for now. All right, let me go ahead and start.
Stuck 2 weeks before, like it's Friday. I didn't even vote for it. Sorry.
All right, last time I talked to you about, we went through some of the equations for the gain and directivity and things like that. What I'm gonna do today, I think I finished with the efficiency of the antenna. Did I do that or not? Do you remember? All right, well, we'll do it now. So when you have an antenna in general, thin wire antenna like this, electrically what it looks like is this. I thought I did this. It has some resistance, and that has to do with dissipation. It's power dissipation. Anytime you have wire, it's not a perfect conductor, so you have resistive losses. You also are going to have something called a radiation resistance. That's the one you like. Radiation resistance has to do with the power actually radiated from the antenna. And then you're also going to have some kind of a reactance. It could be J, X, it could be either a capacitive or inductive effect. It could be either plus or minus J something. Now, that has to do with the near field energies of the antenna that are never launched. And I've mentioned that about near field, the electrostatic or the magnetostatic energies associated with either capacitance or inductance are never launched. That energy just, it comes back, and you can get it back up. So these two are things that burn up energy. And when you have current flowing through here, normally you're going to have some current I naught flowing through the antenna, then your efficient, the total power radiated, you might want to write this down, the radiated power. I did this last time, but I did not give you a homework problem with this on. The radiated power is equal to 1/2 the magnitude of I naught squared times the radiation resistance. That's the radiated power, and it's in watts. And you can put radiated power if you want. Radiated power. Now, the losses, really P loss, is just equal to P dissipation. And that's equal to 1/2 times magnitude of that current I naught squared times R dissipation. So now you get into the factor of efficiency, which I just put E sub F. Thank you very much. Here's yours. Thanks a lot. The efficiency is just equal to the radiated power divided by the radiated power plus the lost power, And if you take a look at that, the 1/2 I naught squared cancel, and you're left with this, and it's a simple thing. It's just the radiation resistance divided by the radiation resistance plus R, and really, in his book, he calls it dissipation. And that's just the losses due to resistive heating of the material. Now, the thing I'm going to tell you about, the higher the frequency, the greater the resistive losses because of the skin effect. You all remember skin effect, how the actual the current sticks to the surface and the resistance gets higher and higher, higher frequency. Now, what you like is a very high radiation resistance. That means a little current can propagate a lot of power. Because remember, the more current, the more loss. That's the one thing you remember. So we would like to make ideally an antenna with a lot of radiation resistance and very little loss. That's our goal. So this is what efficiency is, and based on that, you can say that the actual gain of an antenna is the efficiency times the directivity. Now you can see that directivity has to do with just the mathematically determined by the actual power really, the electric field radiated and then the power, right? That's how you normalize the power. Do you all remember that? And then you integrated the normalized power times sine theta d theta d phi, and you took that, and that was something, if you divided that into 4 pi, and I'm going to do some of these, right? Then you could get the directivity. That was a strict mathematical operation. Here now, that gives you this term, but the efficiency of the antenna is very important for calculating the gain. Now, in any antenna that's intelligently designed, the efficiency is almost 99%. However, there are times when things aren't so intelligently designed, and I have a story for you. I was a part of, at NASA, we were designing a synthetic aperture array, and we were using antennas that were dish antennas, and that I had to design one of them. We're going to have a bunch of these. Or excuse me, not dish, they were patch antennas. And so I designed and it should have had an efficiency of 0.99999%, should have had a standing wave ratio of 1. If you remember standing wave ratio, the higher that is, the worse the actual match is, right? So sent it out to Ball Aerospace, and I wasn't there for the build. We sent it out, somebody fabbed it for us, so we sent it without me taking a look at it. And it goes out to Ball Aerospace for the testing. And they get a standing wave ratio for an efficiency that's like 40 or 50%. So it's like, oh my God. Now remember, what I did was, I did this thing based on mathematical modeling, using it was a finite element routine called HFSS. And everything, if all my assumptions were right, they were perfect, it should have worked. What happened was, one of these techs was in a hurry, and he was soldering on, it's fed with a coax cable. And when he was soldering, he left a big old solder ball about, if you know what I'm talking about when I say soldering, right? Well, solder balls, you try to get rid of all of them. This thing was huge. And he sealed it, so we didn't know it was there, or the guy didn't know it was there. So the guy, smart guy, he's an electrical engineer, who was doing the test. He unpacked it and saw that ball, then he, melted the solder, sucked it off, and said, whoever did this really doesn't know what they're doing, they're dangerous. You had basically stuck an inductor in there, in series with it. And that was how the efficiency became so low. So remember that story. If you're ever building an antenna for anybody, go and test it yourself. Make sure that some idiot didn't do something that's going to destroy the performance. Because when you ship out parts and they don't work, and you're a representative of Adtran looks bad, and you get fired and stuff like that. So remember that story. That's why efficiency to me is important. Because I've had some inefficient builds, and I guess it was my fault for not looking. That's antenna efficiency. Now what we're going to do is this. We're going to get into the short wire antennas. And here we're going to see about some of the formulas and some of the tricks we do mathematically to get the actual electric and magnetic field from this. Now in his book, it's very, doesn't do a lot of development in the theory. You're going to feel it's a little lacking. So I'm going to try and fill in some of the gaps. Didn't I do this last time, by the way?
Yes,
I thought I did. All right, so now we're going to do, these are these are wire antennas, so put down wire antennas. And they're going to start with short ones. And that's electrically short. So you're going to ask, what's that mean? Well, if we have a wire antenna, it's thin wire. The radius of the actual wire does make a difference, but for now you don't have to worry about it. And this antenna has a certain length, L. Almost all thin wire antennas, with very few exceptions, are center fed. There is something called a monopole that is not center fed, but that comes a little later. It's really just half of this. What happens is, for a short wire antenna, when we say it's electrically short, they call this a Hertzian dipole. And that means L is going to be less than lambda over 10. You can put that down. In Whitmore's book, it's just going to have L much, much less than lambda. Well, much, much less interpreted is lambda over 10. Something short. Now, when it's that short, there's a few things that happen in an antenna like this. Basically, you can say that the current is about the same everywhere on that antenna because it's so short. Follow me on this, class? If it's lambda over 10 or less, the current is about the same everywhere. About the same. So if this was the magnitude of the current here versus the length of the antenna, that's about the same. The second thing is this. What we really want from these antennas, I'll write it out here, what we'd like is this. Here's the antenna that has a current I on it, some I naught, and I'm going to go from the center of this antenna a distance r. I'm going to align this antenna on the z-axis so that it makes an angle theta here with the antenna. And what I want to do is get the E field out here, the E field radiated. That's my goal. Now here's how I get it. And I've been contemplating how I'm going to do this without going too far abstract on it. So let me just tell you, I'm trying to hit the high points here of this math involved in this. You're going to have to take some of this on faith. You know how you take Maxwell's equations, they are true and they just happen to be true because of all sorts of experimental measurements, right? Well, this is the easiest way to get at this stuff, and it's going to be based on some mathematical theory that's fairly abstract. So first of all, and I'm trying to get this down without making too much of a problem. Y'all know the divergence of B equals 0. What does that tell us, by the way? There's one single fact that it tells us. There's zero magnetic charge, right? Now that's important. If it was div of D, it would be the rho V, wouldn't it? That would be the electric charge density. Well, there's a mathematical theorem, and this is true, that if you take the divergence of a curl, it is necessarily by definition 0. Does anybody remember that? You've had some vector calculus, right? The divergence of a curl is mathematically 0. Well, so we create this abstraction. It's called the magnetic, it's really a magnetic vector intensity. And its symbol is A. And A by itself means nothing, but if you take the curl of A, you get B. So now we say the magnetic vector potential A is something that is not measurable, not observable, but the curl of it equals the B field. Do you follow me on this? This is a necessary trick. And I gotta tell you this, physicists and mathematicians have spent centuries coming up with clever ways to solve Maxwell's equations and a lot of equations, and this is one of them. So now they say this is true, okay? Here's some of the stuff he doesn't have in his book. So if that's true, then now I do this. I take a look at this is where the next step is. This is not in his book, but I'm adding it just to give you a little better idea. If you go ahead and you take the curl of H, all right, we know that the curl of H is equal to, well, you saw it like this, and I've got a few comments. J plus the partial of D with respect to T. That's the first way you saw that, right? Then I say, as I keep reducing this, we'll do it this way. If I assume sigma 0, then this becomes just curl of H is equal to the partial of D with respect to T, right? And then if I make the case that D is equal to epsilon E here, then I get epsilon times dE dt. And then if I take the phasor domain, d dt becomes j omega. So I have curl of H here is equal to j omega epsilon E. All right? That makes sense to everybody, right? Now, with that in mind, then I can say this curl of H becomes curl, remember, if I have that, then H is equal to 1 over mu curl of A, right there. So curl, if I have curl of H, I really have curl of 1 over mu curl of A is equal to j omega epsilon E. And furthermore, I have curl of E is equal to minus j omega, well, really just minus j omega B. Where I get this is curl of E is equal to minus dB dt. So if I go to the phasor domain, I have this. That means the curl of E is equal to minus j omega. Well, B is curl of A. I hope you appreciate I'm putting this up here just to give you a complete explanation of some of the things he says in his book. So understand, A is a mathematical construct. It's used to get B. It's not something you measure. These are things that physicists do a lot of this stuff. Now if I come down here, just watch this. You all see I can take and group inside the curl operator both E and A. So I can take curl of, and then it would be E plus j omega A, right, equal to 0, if you look at that. You agree with me there? Class? Follow me? Here's something else. If I take a look at this, well, the curl of a gradient of voltage is equal to 0 by definition. I don't know if you know that, but it is. Did you have this, you didn't have vector calculus, did you?
We did, but
Calvary, it's been a while.
Do you all remember some of this stuff?
Somewhat.
All right, this is where this is useful is in these proofs and theorems. Just by themselves, when I took vector calculus, there were a lot of things like Green's theorem and stuff like this, Stokes' theorem. Until you see the applications, it's hard to appreciate what you're doing. This is an application. Now, what this really means is this. Because the curl of this is 0, I can add this term here, and this is the bottom line. Write this down. E, and I better put it up here. There's two things that are going to come of this. First, E is equal to minus the voltage, gradient of voltage, minus j omega A. Now, that's what E is equal to. V is the voltage. I got to tell you this before I go too far afield. Try to understand, I'm trying to give you an appreciation for why I'm putting these things up here. you're gonna see this, and from your perspective, you don't see any kind of linkage to the real world. This is what you had in electrostatics. The gradient of the voltage was equal to E. Do y'all remember that? How many do? All right. The gradient of the voltage is equal to the electric field. Now, that is something in electrostatics that dealt with energy that is non-propagating. It's always linked to the capacitor, right? To the source where the charge exists. This term, minus J omega A, has to do with propagating electromagnetic energy, all right? This term, and this is how you distinguish this. And this is the relationship to E. There's a lot more to be said about this, but it's a little above anything I can do in this class. Now, if I have that, there's one other thing. I've already got A's relationship to H right here, correct? So now I've defined entirely on one vector A, I've defined both H and E for propagating electromagnetic fields. By the way, for propagating electromagnetic fields, this term goes away, all right, when you're talking about propagation. Now I'm going to get into why I said all that and the benefit of this. Hopefully, you'll see some of this. The first time through this, it's a little hairy for anybody. Did you ever use gauge operators in any of your other classes? They create mathematical huh?
Never.
You never did that? Well, this is the way they do it in physics a lot and in engineering to solve these problems, because they're looking for a mathematical, well, actually you did. You use voltage to define E field, right? The voltage is a scalar quantity, and you could take the gradient of that and you get a vector quantity E field. Well, that's the same thing we're doing here. Y'all remember how easy it was to get voltage compared to E field? Voltage was a simple scalar integration. E field was a vector integration. It was much more difficult. But if you had V, you just take the gradient of that, throw a minus sign, and then you're going to have the actual value for the E field. All right, now, that said, now we get down to the nuts and bolts of this. I was going to do the formal equation on this, but I'm going to put this down. We're going to do the whole 9 yards of this. So after all is said and done, what does this mean to us? What we want is A. If we have A, we can easily get H, and if we have H, we can get E. Follow me on this, class? That's the thought process. So what is A in the integral form? Remember before when we had, say, Gauss's law, we had the differential form of Gauss, or better yet, yeah, Gauss's law. Or remember divergence of D is rho V, right? That's a differential form, right? What's the integral form of Gauss's law? The integral of D dot ds is what? The charge inside the actual surface, right? Do you all remember that? There's one is the integral form, the other is the differential. Well, this is the integral form of curl A equals B and so forth. Now, this will be equal to mu, usually it's mu naught over 4 pi. Then it's the integral, write this one down. It's the integral of the length of the antenna. That L is the antenna's length. Of, and here it's I on the antenna, and that's always going to be a function of Z for these problems. They're going to center these antennas at the origin. I'm going to line them in the Z direction. All right? It's just a convenience. It'll be that divided by R, and R is the distance. Maybe I should give you a picture. So if we have this typical thing, this would be the Z-axis. This would be distance R, and we want the E field here, or we want the magnetic vector potential A. This is our angle theta, and here's my antenna right here. And the antenna has a length L. Then it's going to be times E to the minus J beta R, and then it's going to be DL. So in this case it would be DZ, and it would be AZ direction. That's something I'm going to tell you. The magnetic vector potential for a straight wire antenna is always in the direction of the current. Normally what they do here is they'll put a vector here, and they'll just put this as DL. That's what they do, yeah.
What's the integral of L to what?
Now it's going to go over the length of the antenna. You can go from minus L over 2 to L over 2. That's the way it's usually done, because these things are centered. They're center fed. If you're looking in your book, he's going to have something like what I'm talking about. But he's gonna not use I, he'll have J0, and that's the current density. I don't like using that, nobody ever does that. They always put in I because these are thin wire antennas. All right. Now, that's A, and here's where it gets interesting. We're gonna do it now, we're gonna calculate A first based on some assumptions too, and then I'm gonna show you a trick you're gonna thank me for. This is a couple of things I'm going to tell you are stuff that you're not going to find in his book or some of the other books, but they're very useful to know when you're doing real antenna work as far as the theory. So now we start with this problem. We've got an antenna where the length of the antenna is going to be much less than lambda, and I just like to say lambda, or the length of the antenna, L, is going to be less than lambda over 10. Lambda is the free space wavelength. Got it? These are short antennas. So I'm going to have an antenna centered at the origin, on the z-axis, and I have a current I naught on it, and it goes from here to here, all right, from minus L over 2 to L over 2. Now I come out a distance R at an angle theta, and I'm going to get my AZ. Now here's how I'm going to get it. I know that that's true right there. So I'm going to say that AZ is equal to mu 0 over 4 pi. Then it's times the integral of I of z over r times e to the minus j beta r. And this isn't going to be in the AZ direction dz. It's going to go from minus L over 2 to L over 2. Now watch this. This is how this works. Remember I said that I naught is going to be about the same. If it's a short dipole, the magnitude of I all the way up and down that antenna is about the same. That's an assumption. Whether that's true or not is really dependent on the length. If it's lambda over 100, it's absolutely true. If it's lambda over about 10, well, not quite true, all right? Follow me on this? So we're kind of assuming if this is true, what happens? Well, if it's constant over the length of the antenna, then I dz over r right here is a constant, and this whole thing becomes just, and he has this in his book, mu 0 over 4 pi times I naught, because I'm saying that current's a constant there. It's going to be multiplied by e to the minus j beta r over r. Then it's going to be times the length L of the antenna, and it's in the AZ direction. And that's equal to, I mean, that is A. It's only got a Z direction, so it's technically this vector here is the A vector, magnetic vector potential. Now, if we have this in Dr. Whitmer's book, he says it's just a simple matter to get the actual value for the B field, and you can get the B field by going ahead and taking a curl of A. If you have your books, take a look at the very back and look under spherical coordinates, curl. Because what we're going to do is this. We're not going to use AZ right there. We're going to use spherical coordinates. And there's a reason for it, you'll see in a second. But we're going to say that this is really mu 0 I naught times L over 4 pi. And then it's going to be E the minus J beta R over R. And then instead of AZ, I'll tell you this, AZ in terms of the actual spherical coordinates unit vectors, if you think about this, if I'm out at distance, say I'm at an angle theta here, there's actually 2 unit vectors you have to worry about, really 3. If I have a vector AZ here, well, what are the unit vectors in spherical coordinates? You have an AR, right? And then you have perpendicular to that an A theta pointing down. Do y'all see that, class? Just try to understand. I'm not going to try to beat you up on this one. Y'all see what I'm talking about? Now, if I put AZ in terms of these 2 vectors, you can see that minus AZ would be here, right? And the projection onto this would be minus AZ times the cosine of this angle. I hope you can see it. Or I'm sorry, sine of this angle right here. And the projection onto the AR here would be equal to the cosine of this angle right there. I don't know if you can see it, times AR. In his book, he has this. So this becomes equal to cosine of theta AR minus the sine of theta sine of theta A theta. You all see it in his book if you've got it? Can you see it or not? What page is that on? He shows this in his book. You got your book.
Oh, this is not the right book.
Oh,
I've got my book.
never mind. It's in there. And the only thing we've done is take AZ in terms of spherical coordinates, all right? You're gonna see there's a benefit to doing that. So now I come down here and Dr. Wimmer says, well, if we have that, we can apply this curl operator. Here's why I don't like that. Watch. What does this curl operator look like? Look in your book. It's 1 over what? If you look, I'm gonna show you the matrix form that he has. It's 1 over r squared sine theta. So it's 1 over r squared sine theta. Then he has a r, a theta, a phi. Then he goes d dr, d d theta, d d phi. And then down here it's going to be ar, then r, right here, times a theta. Then it's going to be r sine of theta, a phi. Can you all see that in the back of the book? Your book, it's in the very last. It has the spherical form of the curl. Anybody looking at it at all? Very back of your book, you see there they have the curl? Look at the one for spherical, the matrix form. You see it? That's a pain. I'm just telling you it's a pain to do for general things, but there's a better way. Anyway, if you did this, then you would get what he has here. Then you're going to find out if you do that, you end up with finding that, in fact, B is equal to this. It's mu times I over 4 pi, and then he has L times e to the minus j beta r over r, right here. Then it's going to have j beta plus 1 over r times the sine of theta. This is the important part, sine of theta, and it will be in the a phi direction. Now that's equal to b, and he has it in his book. I want you to just take a look at this for a second. I'm going to make a couple things known to you. All right, we got that using A, right? A is a fictitious operator, so mathematical construct that we use to get it. We used a curl operation to get B. Now, once we have B, by the way, this is B, this is the complete B field. It's not just a far field. All right? The 1 over r term is the near field. That would be associated with magnetic energy. This is the complete B field from here, from A. The J beta is going to be the far field term. Now I want you to listen to me. You all see how I have 1 over r out in front, right? So this term, the J beta times sine theta term, falls off as 1 over r. You all see that, class? All propagating electromagnetic fields fall off as 1 over r from the source. All right, that's how they do it, from a singular source. Electrostatic energies fall off as either 1 over r squared or 1 over r cubed. Keep that in mind. Now this, 1 over r times 1 over r is 1 over r squared. You see that? That has to do with energy or power that's going to be linked to the actual current source. It's never going to propagate away that term. That's always going to be bound to the term, to the actual antenna. The thing about this, it gives us something useful. You remember how I said, I just threw it out there, I said, if we wanted to talk about the far field from an aperture antenna, we looked at 2 times the actual diameter, the longest diagonal squared, right? Overlap. Do you all remember that for far field? Here's how we get far field for a wire antenna exactly. We look at this term. Now, when they're equal, when beta in magnitude is equal to 1 over r, that's the point where we divide the regions. Do you all see that, class? Because here, when this term in magnitude is equal to 1 over r, just think about it. Do you all agree that there's going to be propagating power, and there's going to be power that's linked to it, or energy, or however you want to say it, that are going to be the same magnitude? If the magnitude of this term is this, is the magnitude of that. Do you all follow me on this, class? Show hands if you do. What I'm trying to say, if the 1 over r term times everything has to do with energy that's linked, or power that's linked to the antenna, never to propagate, then the J beta term, right here, times all that other stuff, is going to be things that propagate. Follow me? And where they're equal is the point at which you can start saying anything beyond that is going to be far field. Because then it'll just fall off as 1 over r. So if I do this, what is beta? Isn't beta 2 pi over lambda? Now watch. So if I take this and I say 1 over this, so if I have r right here, equal to lambda over 2 pi. That's the point where the energies are the same. What they do for far field is they're going to say R has to be greater than lambda over 2 pi for a wire antenna in order to be in the far field. Even that's not really true. It should be much greater. You should be beyond that by a factor of at least 2, preferably 10. Follow me? And that's how you get far field. What do you notice about this, by the way? This is something very important. Remember with apertures, antennas, the higher the frequency, the further away you had to be? Do you remember that? It was 2d squared over lambda. Look at this one. What happens for these wire antennas? Well, what? The higher the frequency, the shorter the wavelength, right? The higher the frequency, the smaller the distance you have to be away from far field with wire antennas. It's a different relationship. With aperture antennas, the higher the frequency, the further you need to be to get into the far field. But when you talk about thin wire antennas, the higher the frequency, the closer you can be before you're in the far field. That's an important distinction. So I'm going to put that up there. Now, that said, we can, I have a few more things to say. I'm going to just go ahead and give you, based on that H field, we can get the E field. And I'm going to say this, we're going to be talking about propagating electromagnetic energy. So when we have short antennas, this is what I want you to take from that. We can go ahead and we can get the magnetic vector potential, take the curl, although I wouldn't do the curl. I'll show you how to get it without a curl in a bit. And to get the actual B field, and then you can get the H field by dividing the B field by mu. But once you have the H field, you can get the E field by taking minus eta times the direction of propagation, unit vector and the direction of propagation, and crossing that with the H field. I'm going to put this up here next, but I'm going to tell you a shortcut in a second. So keep watching this. So again, short wire antennas, this is a short dipole antenna of length L, has current I0. Here's what you take from this. We care about far field, so write down far field. What is the far field? That's where R is greater than lambda over 2 pi, actually much greater. All right, that's the far field constant. That's how far you have to be away from it. Now, when we have this, we're going to get an electric field, E, and we're going to get an H field. E cross H is the direction of propagation. Actually, I have it that way. E crossed into H would be the direction of propagation, which is the radial direction. So I could say the unit vector in the direction of propagation is AR. Next, we're in the far field. Here's what you take. You're going to get the E field equal to J beta, forget that 1 over R term next to J beta. It's J beta times eta times the current I0, times the length of the antenna over 4 pi. Then there's going to be a phase term, e to the minus J beta R, divided by R. It's inversely proportional to the distance. Then there's going to be the sine operation here, the sine of the angle theta, and it will be in the A theta direction. This is the E field, but it's in the far field. We're not talking about the near field. To get H you can get H by just saying simply it would be really this E field here divided by eta, and the direction would be changed. Instead of being A theta, it would be A phi, and I'm just going to put that down. So that would be equal to J beta I0 L over 4 pi. Here it's going to be e to the minus J beta R over R times the sine of theta, and it would be in the A phi direction. They both vary, they're in phase, they both vary sine theta.
Is that theta the same as the one from before?
Yeah, it's the measurement from the z-axis, yes.
So why do you have the phasor term?
Here?
Yes.
Because
why
it's
is
propagating fields, right?
that? Okay.
E to the minus J beta R has to be there. If you didn't have that, it wouldn't be a propagating wave.
And then for the sine theta,
Huh?
why would you have the sine theta next to that too?
Remember when we did the curl operation, we got a sine theta out of it?
Mm-hmm.
That's where it comes from.
Okay.
It came from the curl of A. A did not have a sine operator, but the curl does.
Okay.
This is what you need to get. All right? Got these two? Work with me now. I have that. Now, The next thing I'm gonna do is talk about some of the things, the characteristics we wanna know about in an antenna. We wanna know the gain of the antenna, directivity, right? Directivity, and we wanna know the radiation resistance. This is important. Does everybody capture that? All right. Now, my assumption so far was that we're in the far field. The other assumption was it's a short antenna and the I value is the same on it. All right. So that's an assumption. Now, if that is true, next thing I can get is the radiated power density. I can get P, or actually I can get actual power density, PAV, and that's 1/2 the real part of E cross H conjugate. Now, I never use that one. For PAV here, that's really the Poynting vector. I've mentioned that before. I use simply 1/2 the magnitude of the E field squared divided by eta, and I know it's propagating in the radial AR direction. I know this seems like to be going fast, but this is a standard equation, right? Now, that's the average power density. Follow me? At any given distance R. When I do this, I'm going to get 1/2, right? Leave eta down here. When I take the E field squared, I want you to notice what happens. When I take the E field squared, that phase goes away, that phase goes away. I have this term, beta I naught L over 4 pi, and there should be, I'm sorry, this is E field. I'm going to have beta times eta I naught L over 4 pi, forget the phase term, that's all squared. So I have beta right here, eta I naught L over 4 pi. That's all squared, and then I have the sine squared of theta divided by r squared is equal to PF. Y'all follow what I've done here? The e to the j business goes away when you take a magnitude and square it up here. Magnitude of the E field squared, okay? Please watch this. This is important. Now that's the average power density, right? Remember, when we're trying to find directivity, we want the normalized power, right? And I always tell you make R equal to 1. Remember that? How I told you to do that? How many do? Do you all remember that? These are tricks. They're useful tricks. So that means I want the normalized power density. It's not going to be a function of R. So if I look at this right here, what's the maximum value can have versus angle? Well, I'm sorry. Let me just state that. Everything that's a coefficient of sine squared theta is a multiplier in front of that, right? You see, when you take the maximum amount, it would be when sine of theta is 1, right? So if I divide the maximum amount into the function, I'm left with the normalized power density being simply the sine squared of theta. Can everybody see that? Follow me on this, class? When I talk about normalized power density, you find the magnitude of this thing, great as possible, and you divide that into the actual formula as a function of angle. How many got this right here? Are you with me? It just means, this thing's got maximum value can have is 1. That's all it means. Got it? Now, once we have this, we find the directivity, D. Directivity, by definition, is 4 pi over what's called the beam solid angle. And that's just the integral, double integral, from 0 to 2 pi, from 0 to pi, of the normalized power density. I'm going to do this one. I don't do them all, but I'll do this one. Times sine of theta, d theta, d phi. And that goes in here. Do y'all remember doing this? I gave you some problems on this. So for this one, let's go ahead and do it. The normalized power density is sine squared, right? I'm going to just do this one for everybody's sake. So if I come over here, I'd say this, the beam solid angle right here, would be equal to the integral from 0 to 2 pi, the integral from 0 to pi, of the normalized power density is sine squared, and then it's times sine of theta, d theta, d phi. Do you all see this, class? I just replaced the normalized power density with sine squared of theta. Now here's the thing, this integral, by now you have calculators that do a symbolic integration. It's almost a moot point to do this, but one time is kind of important you at least see this stuff done, because some of the integrals you're going to run into, I don't know if they have closed form solutions. You have to understand this. So if I integrate this, do you all agree when I go d phi from 0 to 2 pi, I just get 2 pi? because nothing in here is a function of phi class. Then I'm left with sine squared theta times sine theta. Well, the integral from 0 to pi, sine squared is best represented as 1 minus cosine squared theta, b. And then put sine theta here, and then d theta. Now, the reason I did that, and this is a classic way to do it, because now this looks like a u du, doesn't it? If you say that u is equal to cosine of theta, then du is equal to minus the sine of theta, d theta. Follow me on this? So if I do that, then I have 2 pi times the integral. All right, when theta is equal to 0, cosine of 0 is 1. When theta is equal to pi, cosine of pi is minus 1. Then I have here sine theta d theta, which would be equal to minus du, so there's goes a minus sign there, and it's du. And then I have 1 minus u squared. Y'all give me that, class? I'm just representing the integral correctly. Agreed? Work with me here. I'm trying to get this in the lecture time. If I got a minus sign, if you know me, what do I usually do to get rid of that minus sign? Flip the limits, and that's what I'm going to do here. So this becomes plus, and this becomes minus. Follow me, and I'll get rid of it. Now, if you look at this, that's 2 pi times, when I integrate just du, I get u, right? U evaluated from 1 minus a minus 1 is just 2, isn't it? That's the first part of the integral, it's du, right? Then I have u squared du. The integration of that is u cubed over 3, right? U cubed over 3. Well, 1 cubed is 1, minus 1 cubed is going to be plus 1, or this is going to be 2 here. So now I have 2 pi times 2 minus, and this is going to be 2/3. And so that's really what? That's 4 halves minus 2 halves, right? What does this whole thing come down to? That's going to be 8 pi over 3. Bottom line is this whole integration here causes the bottom to be 8 pi over 3. So I have 4 pi over 8 pi over 3. Now when you do the math on this, it's going to be equal to 3 halves, or 1.5. 1.5, and that would be the directivity. So that's the directivity of a short dipole antenna. Not capital D, just D. Now, again, that directivity is the maximum directivity, right? Please listen. So if I have the maximum directivity, if I want the directivity at any angle, the only thing I do is take D max, and I multiply it by P normalized of theta and phi, and now I have the directivity for all angles, theta and phi. So remember the normalized power density was sine squared, right? If I take sine squared times 3 halves, that is the directivity for any angle for a short dipole oriented in the z direction. And I didn't get all the way, I didn't get to show you the trick, how to not have to do another crazy curve, but I'll do it next time. And I'm going to give you some homework on this for Monday. Please do it. All right, any questions before you leave?